All right, some more quantum stuff coming at you here, the wave particle duality, so on, consequences of this, the Heisenberg uncertainty principle. And as a bonus, a possible explanation of diffraction. I should add in here of particles. We thought of diffraction as a wave property previously. You're going to see now, finally, that it can be explained in terms of particle properties, quantum particles, that is. So yeah, particles are observed to be behaving like waves, the slit interference patterns and so on with particles, right? So if everyday particles like tennis balls behave the way small quantum particles do, each time you look to see where the ball was or is or whatever, it would be in a different spot. So if, say there were 3 possible locations, my laptop to delete this box. Here we go. If there are 3 possible locations, the wave equations would predict precisely the percentage of the time you'd find the ball at each location. Might look something like that. And what do we got here? Yeah, it's easy to see this reality with small particles, but not likely to happen with bigger particles, as it turns out, right? So yeah, I don't know about you, but I find that very strange. But this is what small particles do. Very bizarre. So why are there probabilities, right? So weird. Heisenberg realized a strange consequence of all this stuff, and consequence of light being quantized and made up of particles and having wave properties and so on, right? The consequence is known as the Heisenberg uncertainty principle. And so it is that a particle's exact position and velocity cannot be known with precision. So it turns out that the more precisely known the position of a particle is known, the less you can know about the velocity and vice versa. So where an object is and or where it is going can be predicted very successfully using the wave equations mentioned yesterday, of course. But the exact precise, position and velocity cannot be known simultaneously, and I'm going to show you why. Okay, so the reason came from realizing that the act of looking to see the position of a particle involves interacting with it. Okay, so for example, you might bounce light off of it, right, to literally see where it is. This interaction, of course, disturbs the velocity and the position, really. If you try to reduce this interaction disturbance, you're limited by the wave-particle properties of light and wave-particle properties of everything, as it turns out, according to de Broglie and all the evidence that supports it, right? So first, if we used less bright light, right, doesn't reduce anything at all since light is arriving as particles, right? So, a particle has to hit it to observe it. So less bright light or dim light just consists of the same particles, just less of them. So if you're going to identify its location with 1 particle, doesn't matter. You just have to wait longer for that particle to get there. I guess if they're emitting 1 every 5 seconds, you might have to wait 5 seconds for it to be released or whatever, right? But still going to be the same disturbance. What about reducing the energy of each of the particles of light? So as it turns out, energy is related to frequency, right? So we could reduce the disturbance by reducing the energy, right? But if you think about the wave properties, you would need lower frequency photons, which would make the wavelengths longer, right? And if the wavelengths are longer, then that means that the region of space that the position can be pinpointed to is bigger. So you get to know the velocity better, but you suffer, your knowledge about the location suffers. So yeah, it disturbs velocity less, so you know more about the velocity, but as a result, you know less about the position. The opposite of this, if you use high frequency light, you know more about the position because it's smaller wavelength, but it disturbs the velocity more because it's higher energy. So yeah, it's just the result, right? So the Heisenberg uncertainty principle is a consequence of the fact that things that we think of as particles are actually also waves. It's the wave properties that lead to the probabilities and the uncertainties, as mentioned, that I asked about earlier. This video is okay. Just gotta put my disk in. I'm just gonna pause for a quick second.
Quantum mechanics is weird, right? But did you know that some of its supposed peculiarities are not unique to quantum physics, but are just properties of waves in general? Take the uncertainty principle. It says that the better we know where a particle is, the less we know about how fast it's going. There's a limit to how much we can know. But this isn't just quantum weirdness, it happens all the time with normal everyday waves. Remember that the frequency of a wave is how close the wave crests are to each other. A low-frequency wave doesn't have nearly as much oomph as a high-frequency one. And the position of a wave is, well, where the wave is, mostly. So where exactly is a wave? It's spread out everywhere, right? Okay, but for a wave pulse, it's pretty easy to see where the wave is. So now that we know where the pulse is, what's its frequency? Well, a localized pulse doesn't really wave, so we can't measure the frequency of its crests. And that's the uncertainty principle in a nutshell. You can either know where a wave is or where it's going, but not both at the same time.
It's okay. I was looking for something better, but I was looking for a video that would show and illustrate the idea of interacting with something with a long wavelength versus a short wavelength. And this long wavelength light means you're not going to be able to tell where it is as closely, but you'll disturb it less and so on. Couldn't find anything though. Anyways, so yeah, this is what introduced probability into the fundamental properties of the universe, right? Particles that show noticeable, or that show the true quantum nature of reality in a noticeable way, right? The small stuff, where are we at here? Do not have specific positions and velocity simultaneously. The philosophy behind this is that if you can't know something, it's because it doesn't exist, right? There's a lot of philosophy in this kind of physics. Philosophers actually think about this and they're like, okay, well, if that's the case, then if you can't if you can't measure these things, if you can't determine these things, it's because it doesn't exist. It's the idea. So instead, they have wave properties and probabilities of certain locations and so on, right? So it's not just you can't measure it; it's that they actually don't have it. Is what the philosophy would point towards. Yeah, so it's weird stuff, of course, right? Luckily, it can help our analysis of interference patterns, though. So experimental results, photons and electrons and other small particles, form this interference pattern, even if they're sent in one at a time, right? But each single particle, has to be able to interact with both slits and so on. But that's possible if they don't have a precise location, right? I guess, sort of, whatever that means. Anyways, exactly. Here's that joke from yesterday, right? So do you know where you're going? You'd be like, no, but I know where I am, right? That's the joke about the not being able to know the position and velocity simultaneously. Here's the Heisenberg Department of Physics. You're probably here. You have a probable chance of being in this area the most and other areas. Buy tickets here for the lecture on Heisenberg uncertainty principle. I can tell you the time or the place, but not both. No, officer, I don't know how fast I was going, but I know exactly where I am, similar to that first one I showed you about. I can tell you the status of your order or the location, but not both. Heisenberg's Burger Hut or something. Website wants to know your location, allow, and then later on, then it asks the next question, I want to know your momentum, and it's like, nice try, you can't know that. Anyways, just silly. Another explanation of that the uncertainty principle gives us is possibly diffraction of particles, right? So I say possibly because I think it's one of those hard to know at a fundamental level what's really going on, but it makes sense in terms of the Heisenberg uncertainty principle. So previously we thought of it as a wave property and waves spreading out and so on, although we never really talked about what those wavelets really are, but they're weird, right? If light really is particles, though, they can't spread out, right? They remain as a single at a single location, but quantum uncertainty would be the answer. When light going through a narrow slit, its location is determined more and more accurately. Therefore, what? Well, if you know the location more accurately, the trade-off would be you know less about the velocity, right? So, picture the velocity was very defined as straight sideways, and then afterwards it could be lots of different things. The probabilities, it spreads. Probability would change, or the velocity would become less known, so it would deviate, right? So the light particles' paths spread out. They diffract, right? So this makes sense, I guess, right? Here's a little video on it.
Today, I'm doing an experiment that demonstrates Heisenberg's uncertainty principle. So here I have a green laser, and I'm firing it down towards the front of the room through a narrow slit. Now that slit can be adjusted, so it could be made narrower or wider. And the laser spot is projected onto a screen behind it. So what do you think is going to happen to this spot on the screen as I narrow the slit? Well, let's have a look. where you see exactly what you'd expect. The spot gets narrower and narrower. The sides are getting cut off by the slit. Makes complete sense. And if you stop there, you would never realize that Heisenberg's uncertainty principle is at work. But if you keep going, something strange happens. As you make the slit even narrower, the spot starts to spread out. Isn't that incredible? You're making the slit narrower, and yet the spot on the wall is getting wider. The narrower you make it, the wider that spot on the wall becomes. To understand this, we have to look at Heisenberg's uncertainty principle. Heisenberg's uncertainty principle is normally written as delta x delta p is greater than or equal to h on 4 pi. So what does this mean? Well, it's about the position and the momentum of a particle. So x is the position of the particle and p is its momentum. So delta x is the uncertainty in position and delta p is the uncertainty in the momentum. Now, if you multiply those two quantities together, they must always be greater than or equal to h on 4 pi. Now, h is Planck's constant, and that deserves a video all to itself, like this one by 60 symbols. But for our purposes, it's just a very small number. So in our everyday lives, we don't come up against this uncertainty relation because everything is much, much bigger than h. But as we narrowed the slit, we were decreasing delta x for those photons. So we were getting more and more precise about where the photons were passing through that slit. And at a certain point, you come to this limit, so that if you narrow this any further, you're going to break this uncertainty relationship. So what needs to happen is the uncertainty in momentum needs to go up. I should specify this is uncertainty in momentum in the x direction, in the horizontal direction. So if before photons were going perfectly straight, now they must veer off to the left or to the right to ensure that we don't break Heisenberg's uncertainty relation. And the more you decrease your uncertainty in position, the more narrow you make that slit, the more the uncertainty in momentum has to go up. And so if these photons are going to the left and the right, that's going to produce a much wider beam. It's really, really non-intuitive, but it's the way the world works.
It must be the sun playing tricks with my mind.
What about, here's really going to test you, right?
I don't know.
Tell me about what's on that card. Well, this is before you put it up. Only a few blocks from here.
So what do you expect that we'll see over here?
In October 8:31.
I've got to say a big thank you to Professor Walter Lewin at MIT. He inspired me to make this video. And I also have to say a big thanks to the University of Sydney for letting me use their equipment, and especially to Tom and Ralph for helping me set this all up. Oh, and just one more thing. I should point out that this explanation of the experiment is slightly controversial, at least in that Henry from Minute Physics and I have been debating whether it's really that counterintuitive. I mean, if you see light as a wave, then all light is doing here is diffracting. That's the phenomenon where if a wave passes through a slit, it bends at the corners and radiates out in all directions, and that explains the spreading of the beam. But that goes to the very nature of light. Is it made of waves or particles? That's something that I would like to explore in the coming weeks, so stay tuned for that. But Henry has an excellent video about Heisenberg's uncertainty principle, which I think makes it more intuitive and less spooky. So if you want to check that out, click on the annotation.
There's the one we just watched. There was like, it's okay. This is from quite a while ago. So young version of Derek there and Veritasium. So although uncertainty has helped explain some things, how particles can go through two slits and how particles can diffract, it implies some pretty strange things about the world around us. Luckily just for very small stuff, but I mean, what's the boundary between those, right? You saw in the other video where the guy was saying he's convinced that we're going to observe this stuff directly. I'm not so much, but anyways, I think the idea, if you think of it, is, to get all 60 molecules of the buckyball, 60 carbon atoms, to all have their chance of appearing on the other side of a barrier or whatever we're talking about. Just very, very small, right? So you can see it easily for small, single, particles, because if it happens, you notice it. Whereas, if you have two particles bound together, they both have to happen to end up in that spot, or something like that. I know, it's weird. Anyways, another excerpt from The Elegant Universe for us here. What it would be like if the world behaved this way at a big scale. So These George and Gracie, we're going to meet them when we talk about special relativity. Okay, so they're going to go on a journey, and we're going to learn all about special relativity. So they're back from that trip, teaching us learning about special relativity, and they're heading over to the H bar for some refreshments. Remember this author, and I mistakenly was saying H bar instead of just H as well. They're not actually the same thing, right? But H divided by 2 pi, kind of same. Anyways, they're at the H bar, and George orders the usual: a papaya juice on the rocks for himself and a vodka tonic for Gracie, and kicks back in his chair, hands clasped behind his head to enjoy a freshly lit cigar. Just as he prepares to inhale, though, I don't recommend any of these things, by the way, he is stunned to find that the cigar has vanished from between his teeth. Thinking the cigar must have somehow slipped from his mouth, George sits forward, expecting to find it burning a hole in his shirt or his trousers pants. But it's not there. The cigar is not to be found. Gracie, roused by George's frantic movement, glances over and spots the cigar lying on the counter directly behind George's chair. Strange, George says. How in the heck could it have fallen over there? It's as if it went right through my head, but my tongue isn't burned, and I don't seem to have any new holes. Gracie examines George and reluctantly confirms that his tongue and head appear to be perfectly normal. As the drinks have just arrived, George and Gracie shrug their shoulders and chalk up the fallen cigar to one of life's little mysteries, but the weirdness at the H bar continues. George looks into his papaya juice and notices that the ice cubes are incessantly rattling around, bouncing off of each other and the sides of the glass like overcharged automobiles in a bumper car arena. And this time he's not alone. Gracie holds up her glass, which is about half the size of George's, and both of them see that her ice cubes are bouncing around even more frantically. They can hardly make out the individual cubes. Oh boy, there we go. As they all blur together into an icy mass, but none of this compares to what happens next. As George and Gracie stare at her rattling drink with wide-eyed wonderment, they see a single ice cube pass through the side of her glass and drop down to the bar. They grab the glass and see that it's fully intact. Somehow the ice cube went right through the solid glass without causing any damage. Phew, must be post-spacewalk hallucinations, says George. They each fight off the frenzy of careening ice cubes to down their drinks in one go. I don't know if I would have done that. And head home to recover. Little do George and Gracie realize that in their haste to leave, they mistook a decorative door painted on the wall of the bar for the real one. The patrons of the H bar, though, are well accustomed to people passing through walls and hardly take note of Gracie and George's abrupt departure. A century ago, while Conrad and Freud were illuminating the heart and darkness, soul of darkness, the German physicist Max Planck shed the first ray of light on quantum mechanics, a conceptual framework that proclaims, among other things, that the H bar experiences of George and Gracie, when scaled down to the microscopic realm, need not be attributed to clouded faculties. Such unfamiliar and bizarre happenings are typical of how our universe, on extremely small scales, actually behaves. So the reason for the uncertainty explained again here, and the reasons for George and Gracie's strange observations. If the H bar was, if H bar or really just H was a bigger number, right? So if H, Planck's constant, was a larger number, and the uncertainty would be that kind of uncertainty in this stuff would be observable for larger objects. So it says, by now you should have some sense of the dramatically new way that the universe works according to quantum mechanics. If you have not as yet fallen victim to Bohr's dizziness dictum, the quantum weirdness we now discuss should at least make you feel a bit lightheaded. Even more so than with the theories of relativity, it is hard to embrace quantum mechanics viscerally. So the relativity stuff we're going to see next. And like I said, it's weird, but I mean, it's a direct consequence of some pretty concrete things, let's say. So yeah, to think like a miniature person born and raised in the microscopic realm, we just can't do that. And you know, we try to visualize what might be happening at that level, but again, it's all theoretical, all possibilities. You know, there is though one aspect of the theory that can act as a guidepost for your intuition, as it is the hallmark feature that fundamentally differentiates quantum from classical reasoning. It is the uncertainty principle, discovered by German physicist Werner von Heisenberg. Maybe it doesn't have a von in there, but Heisenberg, that sounds good, right? in 1927. So it's the Heisenberg uncertainty principle. Different Heisenberg than the TV show, by the way. Obviously, I picked that name because of his knowledge of quantum physics and knowing about Heisenberg. If you know what I'm talking about, you know. This principle grows out of an objection that may have occurred to you earlier. We noted that in the act of determining the slit through which each electron passes, its position necessarily disturbs its subsequent motion, its velocity. But just as we can assure ourselves of someone's presence by either gently touching them or by giving them an overzealous slap on the back, why can't we determine the electron's position with an ever gentler light source in order to have ever decreasing impact on its motion? From the standpoint of 19th century physics, we should be able to, right? Classical physics, we should be able to do that. By using an ever dimmer lamp or an ever more sensitive light detector, we can have a vanishingly small impact on the electron's motion. But quantum mechanics itself illuminates the flaw in this reasoning. As we turn down the intensity of the light source, we know we're just decreasing the number of photons. Once we get down to emitting individual photons, we cannot dim the light any further without actually just turning it off. There's a fundamental quantum mechanical limit to the gentleness of our probe or our light. And hence, there is always a minimal disruption that we cause to an electron's velocity through our measurement of its position. Well, that's almost correct. Planck's law tells us that the energy of a single photon is proportional to its frequency. We know that already. Inversely proportional to its wavelength. And by using light of lower and lower frequency, and therefore larger wavelength, we can therefore produce ever gentler individual photons. But here's the catch. When we bounce a wave off an object, the information we receive is only enough to determine the object's position within a margin of error equal to the wavelength. To get an intuitive feel for this important fact, imagine trying to pinpoint the location of a large, slightly submerged rock by the way it affects passing ocean waves. As the waves approach the rock, they form a nice orderly train, one up and down cycle followed by another. After passing the rock, individual wave cycles are distorted, a telltale sign of the submerged rock's presence. You may have experienced this on a lake if you're a boater or whatnot in the summer. But like the finest set of tick marks on a ruler, the individual up and down wave cycles are the finest units making up the wave train, and therefore by examining solely how they are disrupted, we can determine the rock's location only to within a margin of error equal to the length of the wave cycles, that is, the wave's wavelength. In the case of light, the constituent photons are, roughly speaking, the individual wave cycles, with the height of the cycles being determined by the number of photons, whatever. A photon, therefore, can be used to pinpoint an object's location with only one precision of one wavelength. We think of it better as we know it has wave properties, right? This is a different book, different time, whatever. But the Broglie wavelength to do with the photon, we know it exists, right? And there's a proportionality between that and the frequency, or that and the energy, I should say, really. So yeah, we are faced with the quantum mechanical balancing act. If we use high frequency short wavelength light, we can locate the electron with greater precision, but high frequency photons are very energetic, equals h bar f, right? Or just hf, actually. Old habits die hard. And therefore sharply disturb the electron's velocity. If we use low frequency long wavelength light, we minimize the impact on the electron's motion, since the constituent photons have comparatively low energy, but we sacrifice precision in determining the electron's position. Heisenberg quantified this competition and found a mathematical relationship between the precision with which one measures the electron's position and with which one measures the velocity. He found, in line with our discussion, that each is inversely proportional to the other. Greater precision in precision necessarily entails greater imprecision in velocity measurement, and vice versa. And of uttermost importance, although we have tied our discussion to one particular means for determining the electron's whereabouts, Heisenberg showed that the trade-off between precision of position and velocity measurements is a fundamental fact that holds true regardless of the equipment or the procedure employed. Unlike the framework of Newton or even Einstein, in which the motion of particles is described by giving its location and velocity, quantum mechanics shows that at a microscopic level, you cannot possibly know both of these features with total precision. Moreover, the more precisely you know one, the less precisely you know the other. And although we have described this for electrons, the ideas directly apply to all constituents of nature. And of course, the idea if you can't know it, then it doesn't exist, right? The philosophy of it. Einstein tried to minimize this departure from classical physics by arguing that although quantum reasoning certainly does appear to limit one's knowledge of the position of velocity, the electron still has a definite position of velocity, exactly as we've always thought. But during the last couple of decades, theoretical progress spearheaded by the late Irish physicist John Bell and the experimental results of Alan Aspect and his collaborators have shown convincingly that Einstein was wrong. Electrons, and everything else for that matter, cannot be described simultaneously as simultaneously being at such and such location and also having such and such speed. Quantum mechanics shows that not only could such a statement never be experimentally verified, as explained above, but it directly contradicts other, more recently established experimental results. In fact, if you were to capture a single photon in a big solid box and then slowly crush the sides to pinpoint its position with ever greater precision, you would find the electron getting more and more frantic. Its velocity would be fluctuating more and more, almost as if it were overcome with claustrophobia. The electron will go increasingly haywire, bouncing off the walls of the box with increasingly frenetic and unpredictable speed. Nature does not allow its constituents to be cornered. In the H-bar, where we imagine H or H-bar, whichever, to be much larger than in the real world, thereby making everyday objects directly subject to quantum effects. The ice cubes in George and Gracie's drinks frantically rattle around as they suffer from the quantum claustrophobia. Although the H-bar is fantasyland, in reality, H is very small, and precisely this kind of quantum claustrophobia is, it says, but, what's here? Although H-bar is fantasyland, in reality it's very small. Precisely this kind of quantum claustrophobia is a pervasive feature of the microscopic realm. The motion of microscopic particles becomes increasingly wild when they are examined and confined to ever smaller regions of space.
We don't notice the strangeness of quantum mechanics in everyday life, but it's always there if you know where to look. You just have to change your perspective and get down to the tiniest of scales, to the level of atoms and the particles inside them. Down at the quantum level, the laws that govern this tiny realm appear completely different from the familiar laws that govern big, everyday objects. And once you catch a glimpse of them, you never look at the world in quite the same way. It's almost impossible to picture how weird things can get down at the smallest of scales. But what if you could visit a place like this, where the quantum laws were obvious, where people and objects behave like tiny atoms and particles? You'd be in for quite a show. Here, objects do things that seem crazy. I mean, in the quantum world, there's a sense in which things don't like to be tied down to just one location, or to follow just one path. It's almost as if things were in more than one place at a time. And what I do here can have an immediate effect somewhere else, even if there's no one there. And here's one of the strangest things of all. If people behave like the particles inside the atom, then most of the time, you wouldn't know exactly where they were. Instead, they could be almost anywhere until you look for them. Hey, I'm gonna have what he's having. So why do we believe these bizarre laws? Well, for over 75 years, we've been using them to make predictions for how atoms and particles should behave. And in experiment after experiment, the quantum laws have always been right.
It's the best theory we have.
There are literally billions of pieces of confirming evidence for quantum mechanics.
It has passed so many tests of so many bizarre predictions.
There's no disagreement between quantum mechanics and any experiment that's ever been done.
The quantum laws become most obvious when you get down to tiny scales like atoms. But consider this. I'm made of atoms. So are you. So is everything else we see in the world around us. So it must be the case that these weird quantum laws are not just telling us about small things. They're telling us about reality.
Suppose you drop a ball down the side of a valley. Classical wisdom tells us that when the ball rolls up the hill on the other side, it can't go any higher than the height from which you dropped it. That's conservation of energy. Even if there's a nice big long slope to roll down on the far side of the mountain, the ball just can't get there, unless you give it enough energy to get over the barrier. But in quantum mechanics, things work a little differently. You see, the quantum world is probabilistic, so if you release a particle in a valley, chances are the next time you see it, it'll still be somewhere in that valley. But if there's a nice big slope to roll down on the far side of the mountain, well, that's a place the particle would really like to be. And it turns out, there's also a small chance that's where you'll find it. If this isn't crazy enough, it's even possible you'll find the particle in the middle of the mountain. And in real life, this means that an electron sometimes hangs around inside the nucleus of an atom. Did you know that if the sun were fueled by combustion of, say, gasoline or wood, it would burn out in just a few millennia? So how is it still here after 4.5 billion years? Physics. The sun is like a big nuclear submarine. In the sky. That's right, it's fueled by nuclear reactions that fuse hydrogen atoms together into helium and other heavier elements, releasing huge amounts of energy in the process. In this way, the sun is slowly converting its mass into energy, in the form of sunlight, and it has more than enough fuel to last billions of years. But nuclear fusion's no walk in the park. On Earth, we need to heat hydrogen up 100 times hotter than the sun to get a fusion reaction. So how does the sun do it? Quantum tunneling. There's a small chance, which I'll explain later, that hydrogen atoms, even if they aren't quite hot enough for fusion, will fuse together anyway. And the sun is so big and has so much hydrogen that these small chances happen all the time. And that's what keeps the sun energized. So when the sun shines tomorrow, give thanks to quantum mechanics.
All right, so I skipped this video because we watched it previously. This is the one where they showed like the buckyballs and the guy talking about how he's convinced that we'll be able to observe quantum mechanics in large scale and so on. I went on to quantum tunneling. And so the two videos we watched there were about quantum tunneling. Yeah, so I'll read the stuff about it as well here and help it all make sense. But the uncertainty principle also gives rise to a striking effect known as quantum tunneling. Fire a plastic pellet against a 10-foot thick concrete wall. Classical physics confirms, of course, what your instincts would tell you will happen. The pellet will bounce back. The reason is that the pellet simply does not have enough energy to penetrate such a formidable obstacle. But at the level of quantum particles, quantum mechanics shows unequivocally that wave functions, that is, the probability of waves of particles making up the pellet, all have a tiny piece that spills out through the wall. This means that there is a small, but not zero, chance that the pellet actually can penetrate the wall and emerge on the other side. How can this be? Well, the reason comes down once again to the Heisenberg uncertainty principle. To see this, imagine you're completely destitute and suddenly learn that a distant relative has passed on in a far-off land, leaving you a tremendous fortune to claim. The only problem is that you don't have the money to buy a plane ticket to get there. You explain your situation to your friends, if only they will allow you to surmount the barrier between you and your new fortune by temporarily lending you some money for a ticket. You can pay them back handsomely after your return, but no one has the money to lend. Remember, though, that an old friend of yours works for an airline, and you can implore him with the same request. Again, he cannot afford to lend you the money, but he does offer a solution. The accounting system of the airline is such that if you wire a ticket payment within 24 hours of arrival at your destination, no one will ever know the difference. So in this way, you're able to claim your inheritance. The accounting procedures of quantum mechanics are quite similar. just as Heisenberg showed that there is a trade-off between the precision of measurements of velocity and position, he also showed that there's a similar trade-off in the precision of energy measurements and how long it takes to do the measurement. Quantum mechanics asserts that you can't say that a particle has precisely such and such energy at precisely such and such moment in time. Ever-increasing precision of energy measurements require ever longer durations of time to carry them out, roughly speaking. This means that the energy a particle has can wildly fluctuate so long as this fluctuation is in a short enough time scale. So just as the accounting system of the airline allows you to borrow money for your plane ticket, provided you pay it back quickly enough, quantum mechanics allows a particle to borrow energy so long as it can relinquish it back within a time frame determined by the Heisenberg uncertainty principle. The mathematics of quantum mechanics shows that the greater the energy barrier, the lower the probability, and this creative microscopic accounting will actually occur. But for microscopic particles facing a concrete slab, they can sometimes and do sometimes borrow enough energy to do what is impossible from the standpoint of classical physics, momentarily penetrate and tunnel through a region that they do not initially have enough energy to enter. As the objects we study become increasingly complicated, consisting of more and more particle constituents, such quantum tunneling can still occur, but it becomes very unlikely since all of the individual particles must be lucky enough to quantum tunnel together. So that's the idea of complex particles having less likelihood of showing quantum effects. They must all be lucky enough to tunnel together. But shocking episodes of George's disappearing cigar and ice cubes passing right through the walls of a glass and George and Gracie's passing through the wall and so on can happen in a Fantasyland land such as H-bar, in which we imagine the Planck's constant H as really large. Such quantum tunneling is commonplace, but the probability rules of quantum mechanics, and in particular the actual smallness of H in the real world, show that if you walked into a solid wall every second, you would have to wait longer than the current age of the universe to have a good chance of passing through it on one of your attempts. With eternal patience and longevity, though, you could sooner or later emerge on the other side. The uncertainty principle captures the heart of quantum mechanics, features that we normally think of as being so basic as to be beyond question, that objects have definite positions and speeds, and that they have definite energies at definite moments. They are now seen as mere artifacts of Planck's constant being so tiny on the scales of everyday world. Of importance is that when this quantum realization is applied to the fabric of space-time, it shows fatal imperfections in the stitches of gravity and leads us to the third and primary conflict physics has faced during this past century. I just have to wait for the screen to go because my microphone died out, so I'm narrating over right now. There we go. So quantum tunneling. Link it to the size. Properties observed here. Tunneling apparatus. So, larger objects are made up of tiny. So large objects are made up of a bunch of tiny particles, right? And so to have them all line up and quantum tunnel at the same time would be very unlikely. Black holes, though, pretty cool. You've probably heard about them. There's gravity so dense that nothing escapes from black holes and so on. Stephen Hawking, his genius was he realized that if a particle near the event horizon had a probability of being located outside of the black hole, it could escape. There's another way that that's described too, the pair production stuff, like it's called spontaneous creation of particle pairs out of free space. As long as it doesn't occur for longer than the Heisenberg time limit, then that's fine too. But either way, Hawking predicted the kind of radiation that would come out of black holes and then got astronomers to go look for it, and they found it, which is pretty crazy. So, yeah. Finish that up here. More long-winded last time, apparently. And here I show a little bit of a drawing about tunneling microscopes, electron microscopes. There we go. So you have a probe, and there's an electron that's here, or that's a little bit too of a classical physics way of saying it. It has a high probability of being here. Doesn't have enough energy to jump to the surface, right? But there's a non-zero probability of it just being there, right? And so if it appears there, then that current would be registered in the system. The probability of it jumping or being these other spots is extremely sensitive to the distance between the probe of the electron microscope, the tunneling scanning microscope, whatever you want to call it. Extremely sensitive to that distance, and so you get a really, really fine scan of that surface, and that's how they work, basically, roughly speaking. So yeah, that's it. Thanks for watching, and yeah, we'll see you next time.